Hi, I'm Sam Jabley, and you're listening to Lab 4 Magnetic Field of a Bar Magnet in Physics 2212. So before we get started, here's a little introduction. In this lab, the magnetic field of a bar magnet will be measured in various ways using an iPhone app, tape, and a meter stick. And the purpose of this lab is to measure the on-axis and off-axis magnetic field that is distance dependent of a bar magnet and to compare the observed versus predicted distances of those magnetic fields. The lab is going to showcase the Biot-Savart law, how the magnetic field of a dipole works, and the distance dependence formula. So, some details and a little results preview. The system of the experiment is the bar magnet, and the surroundings is everything else. The experimental model is the magnemeter and the meter stick, and the computational model was made using GlowScript. And a little results preview. We found N to be negative 2.318, and the magnetic dipole moment to be 15.015 amps per meter squared, times meter squared. So some fundamental physics principles. We have the Biot-Savart law, and this is the equation that describes the magnetic field that is generated by a constant electric current, and you can see it listed here. We have the magnetic field of a dipole, the limit of either a closed loop of electric current or the field created by two poles, and we have that equation listed right here. And we have the distance dependence formula, and that is the increasing distance causes the magnitude of the magnetic field to decrease, and that magnitude follows the inverse square law, and we have that formula listed right over here. So here's the experiment. Before the experiment could be performed, it must be set up. Step 1 is to orient the phone in a way so that its magnemeter is orthogonal to Earth's field. And once this is done, the magnemeter is found and marked on the phone using tape. Then, the distance between the magnemeter and the magnet can be measured for both on and off axis. And then the data can be measured and recorded. So, the first part is the on-axis measurement, and you can see the data that I collected right here in this spreadsheet. And here you can see the natural log of R compared to the natural log of the magnetic field in the X component. And here you can see it graphed. And using the distance dependence formula, which you can relate to this equation here, you find N to be this number and the natural log of K to be the y-intercept. And once you do some math, you get K is this number. And here's the calculations to find the magnetic moment of the dipole. And basically you set this equation equal to this equation, rearrange for mu, and then just plug in what you know and solve. So you have the off-axis measurement, which is the second part, and it's just more spreadsheet stuff. Put in the data that I collected here and found these numbers. And now we get to the computational model. So I inserted the magnetic dipole moment that was calculated here, and then I edited this function which creates the magnetic field, and then I changed the code for producing the magnetic field arrows and edited the scale and distance, then the observed axis vectors on visualizing the magnetic field on the axis and perpendicular to the axis here. Then down here I changed dperp and d, and then the observed 45-degree vector, and then I changed the code for creating the magnetic field arrow 45 degrees off axis. And this is the results. The arrows are a little hard to see, but here they are. And you can see all the information listed down here too. And so some assumptions and errors. It's assumed that the bar magnet acts as a magnetic dipole and that the magnetic field follows the inverse square law and decreases as distance increases. And the errors are that the magnetometer was likely not found as precisely as possible due to error of measurement. And there's also error of measurement with the meter stick and the electric or magnetic objects that are all around in the lab that were skewing the field in the surroundings. So some observation statements, and this has to do with the distance dependence formula and the inverse square law. When the statement 1 was found to be true, 2 and 3 false, and 4 true, and basically it all follows that inverse square law that the magnetic field decreases as distance increases. And so the discussion questions. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How did the results change? Well, the results would be skewed because Earth's magnetic field would add vector components to the bar's magnetic field, creating a different number. And what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect these measurements to differ? Well, the direction of the field would stay the same, but the magnitude of the magnetic field would double in strength. Thank you for watching. I hope you learned something in this lab, and I'll see you next time.